been zeroed and cal and everything. So let's go over here. And what do we see? There it is. There's our power meter. You can see it's showing minus 46 dBm. It's going to go up and down by a few dB. At this range, it's within the uncertainty of the power sensor itself. I've also done an extensive video showing you exactly what's inside a power sensor. At this range, it's within the uncertainty actually does. Power section itself. I've also done an extensive video showing you exactly what's inside a power sensor. At this range, it's within the uncertainty actually does. Power section itself. I've also done an extensive video showing you exactly what's inside a power sensor. At this range, it's within the uncertainty actually does. Power section very good. Remember, we have also done one can actually increase the power to higher power. Let's see. Let's go ahead to can actually increase the power that's pretty good to higher power 20 dBm. Also good, it's a little bit too high at 20 dBm. Can actually increase the power to higher power 20 dBm anymore. Also now we can engage higher at 20 dBm. Can actually increase the power to higher power 20 dBm. There's minus 10. Now we can engage higher at 20 dBm. Increase the power to higher power 20 dBm. There's minus 10. Now we can engage higher at 20 dBm. Increase the power to higher power 20 dBm. There's minus 10. Now we can engage That's not too bad considering how old the instrument actually is. Now, one of the disadvantages of this type of synthesizers, which most synthesizers actually are, is that they achieve higher frequencies through multiplication. And I've gone through the block diagram so you can anticipate what that would be like if you were to multiply the frequency. So if you're off by about 65 hertz at 1 gigahertz, because we're multiplying it, our error in absolute value is going to grow. So if I go to 2 gigahertz, you can see that now we are off by exactly twice as much, about 130 hertz. And that's to be expected. This is what you would get when you do frequency multiplication. But the architecture of achieving 2 gigahertz from a 1 gigahertz source now becomes a lot easier, of course. But that's normal. That's how it works. So now really the only thing we haven't tested is some of the modulation functions. Of course, there's a lot more to do. But you know, for us, if we get the modulation working, then we're fairly satisfied that the instrument is good. Before we do any IQ measurement and any modulation measurement, let's do an IQ calibration. And if this thing succeeds, this itself tells us that the internal measurement capability and calibration routines are actually working. So that's a good one. Let's wait for this to finish. So the calibration ran just fine. Let's go ahead and analyze a modulation with this instrument. I have a carrier set to 2.5 gigahertz, amplitude is 0 dBm. We're going to take a look at a 256 QAM modulation, single carrier. That's 8 bits per symbol, of course, at a symbol rate of 6.25 megasymbols per second. That's the highest this instrument can do at this modulation rate. So that's still quite a bit of data coming out of this. And then we're going to do a filtering of 0.35 root raised cosine. What else is important here? We're also going to have a PRBS sequence of 2 to the 31, 2 to the 23 minus 1. So everything looks good. Now, how do we analyze the modulation? Well,